here are the main components of getting an amateur radio satellites. You have Doppler shift, different satellite types, bandwidth, antennas, and tracking of the birds. So some of this is going to be a little redundant for some of you, but I figured, just go through it so we're all on the same page. Just real briefly on Doppler shift, that's the effect on waves when the transmitter is moving relative to the receiver. Technologies that are based on Doppler shift, pretty much radar and anything else I found with the word Doppler, didn't find too much. So here's a graphic representation of Doppler shift. So you'd say the transmitter's here in the center, and then if you place the receiver anywhere within this graphic here, these are the sort of characteristics you'll be looking to expect. So this transmitter here in the graphic is moving from left to right. So if you're in front of the transmitter here, your waves are going to be compressed a bit. You're going to receive it at a higher frequency, and vice versa. If the transmitter is moving away from you, your received frequency is going to be lower than the transmitted frequency that's actually coming out of the transmitter. And so how that ties into satellites is pretty much all the amateur radio satellites are low Earth orbit satellites. So Doppler shift correction is pretty key as far as being able to match the receiver and get in there and make a contact. So the two main ways of Doppler shift correction would be software-aided tuning or manual tuning. For software-aided tuning, personally I use Ham Radio Deluxe, has a pretty nice satellite program in it. There's a couple other, I think Sat PC and MacSat I heard is pretty good. Or Mac Doppler is the one for Macs. And there's nothing wrong with manually tuning your Doppler shift. It works great. I started out that way, and especially on the FM satellites, it's not that bad. So here's a kind of a screen capture here of my Ham Radio Deluxe tracking a satellite. So it's SO50 there, and you can see there's about a about a 7 kilohertz difference there on the Doppler shift, and then on the 2 meter band looks like you have about 2 kilohertz there. So the software will automatically correct it, and with the single sideband satellites, some of them have a bandwidth anywhere from 10 to 100 kilohertz. So there's enough space for actually several QSOs to be going on the same pass. And then more so it's about lining your transmission frequency with if you say you take the bandwidth, spread it across here. If you're transmitting over here but you're coming down over here, usually it's easier to try and find yourself where you're transmitting, make sure you're kind of in the same section. Usually you need a duplex radio to be able to do that. I don't use a duplex radio, I use a simplex radio, and it works fine. Now we're kind of going to get into geosynchronous versus geostationary. A geosynchronous satellite is a satellite that completes its orbit around the Earth within 24 hours, so it's very similar to a geostationary, except it's off the plane of the equator. A geostationary satellite's on the same plane as the equator, so it will stay in the sky at all times. So for a geostationary, you don't need any sort of tracking equipment or anything. So any satellite TV, pretty much all satellite services, aside from like Iridium and satellite phones, use geosynchronous. There's some sat phones that use, I'm sorry, the Iridium and sat phones will use a low Earth orbit. That's because of the distance between a low Earth orbit and the geosynchronous. It's quite a far ways out in orbit. So in order for a portable sat phone to be able to communicate to a geostationary or geosynchronous, they have to bump the watts up. So usually most of the geostationary stuff is going to be satellite TV dishes you see mounted aren't moving. So here's a graphical of the geostationary versus the geosynchronous. So So that's going to be your satellite TV, fixed satellite services there. And I think, I'm not sure which services use a geosynchronous satellite, but I would imagine for mobile satellite it would be pretty useful, because if, say we're observing a geosynchronous satellite from our sky in a fixed position, we should be noticing it just go up and down throughout the day. So since it has the same 24-hour orbit, let's say at 10 o'clock it's at 60 degrees above the horizon. Tomorrow at 10 o'clock it should be at 60 degrees above the horizon. So that's one pretty nice thing about that. And at least it's over the same sector quadrant of the Earth at all times. So once it gets down here, you might lose signal, but at least you have a guaranteed time that it's coming back. SKL2 is an amateur radio geostationary satellite. It has a 2.4 gigahertz uplink and a 10 gigahertz downlink. The only kind of sad thing about that is it is over Africa. It would have been pretty nice to have a geostationary satellite over North America. Being able to have 24/7 satellite amateur radio communications, I think would be pretty cool and useful. Over Africa, I'm sure they can, utilize it for more critical communications, because we have a lot more options available here. Low Earth orbit satellites, like I was touching on earlier, are the majority of amateur radio satellites. And I would say there's kind of two main factors with that. As far as the antenna size, on the geostationary, the antennas would have to be much larger. The satellite would cost a lot more to produce. So the low Earth satellites, you can pretty much build them in a CubeSat, pay to put it on a payload, and then they'll just throw you out while they're going up to a different orbit. So it's a lot cheaper to launch a LEO satellite than a stationary satellite. So here's a time lapse of my tracking rig at home. And I'm using a Arrow antenna here on the left. That's for a separate project I'll go into in a second. So I forget, this is probably SO50 or something. So there's me talking to my dad there. The computer's controlling the satellite tracker there. And if you're kind of debating on if going into getting a tracker, I found this computer interface here by the model's called a Fox Delta ST2. So I think the company's Fox Delta. They're out of somewhere in Europe, but the main reason I went with that is because the controller is a third of the price than Yaesu's controller, and it has pretty good reviews on it. And I've been using it for a little over a year, and I have no complaints on it. Thing works absolutely perfect, and no problems there. The kind of three antennas you could use to operate on an amateur radio satellite. The most common one is a Yagi. That's what I use. That's what's over there in the corner. And the Yagis work good. The only problem is most of the LEO satellites are tumbling while they're up in orbit. So you'll notice a slow rise and drop in the signal sometimes. I haven't really had it affect my operation too bad. Noticed it just a handful of times, nothing that's really compelled me enough to switch to a circularly polarized antenna. Though I heard the circularly polarized work pretty good, you don't really have to worry about that. And as far as a parabolic dish, it would definitely be pretty nice to be able to use a parabolic antenna, but to build a parabolic at 2 meters or 70 centimeters, you'd have to have a pretty big dish compared to the same gain you get to a Yagi at that low of a frequency. So the parabolics I usually only use above 1 gigahertz depending on what I'm doing. So here's my Yagi in the backyard here, a duplexer. And let's see, here's a circularly polarized antenna. There's a couple different types. That's an egg beater over there. I'm not sure what the name of if this type of antenna has a name, but basically the goal is to be able to maintain the same signal strength of dBs coming in, even if the polarization is, at different angles or constantly moving. So it definitely helps out. Here's my parabolic antenna. This dish was from, let's see, probably over 5 years ago. I don't know if any of you guys were into the HSMM mesh stuff. It was a really neat project. I personally really enjoyed it. It seemed to lose traction though eventually, and so not much stuff is going on with that. I was thinking now there's some open source LTE softwares coming available. So one thought I've had is being able to operate an amateur-owned LTE network would be pretty cool. Some of the problems is LTE is built around encryption. So there's kind of two ways I could think of getting around that. Either have a straight zero encryption key and publish the encryption keys to get around the FCC guidelines, or figure out a way to disable the encryption altogether. Here's a audio of a FM contact. Do we have audio?
That's a good question.
We'll see in a second.
I hear it.
I think that's a water pipe.
There's a pot, there's a knob on the wall over there, might control the volume, I don't know. Not that one.
I think this the intercom. This one?
Try it.
Break one,
Nope.
That's right. This is the volume channel, yeah.
Volume's all the way up.
He said it didn't work, but I don't believe he was telling me that. PCD,
Well, anyway, basically in the video you can hear the audio quality of the satellite as it starts is at its peak height and then starts to go over. And the one pretty neat thing that I found is that if you have a pretty good pass of a satellite, it can be just as clear as the repeater, and you can have crystal clear audio going over it. And it's pretty satisfying to be able to do that and talk to somebody in Georgia, Tennessee, or something on a satellite and have audio like that. The sideband satellites, I don't have audio for a sideband, but the two, so we have our GEO, our LEO satellites, and then as far as LEO satellites, there's FM satellites and single sideband satellites. And the interesting thing is on the FM satellites, as far as my opinion and my experience, it's more like a contest, throw out your call sign, exchange a signal report, 783 is good luck. And on the sideband satellites, I've had a 10-minute QSO the whole pass, I'm just hanging out on the repeater. So I would say there is a different culture on an FM satellites compared to sideband satellites. This is a member of the JTRG. His name's Larry, and we went out to the park to do a test probably a little over 6 months ago. And I brought the rotator and stuff out there, and we were picking up signal pretty good, but weren't able to make any contacts. Now it was Hamfest in Orlando, so there was a good amount of people on the satellites, but still, it really should have been able to make some sort of contact. So the first thing I found that was kind of affecting our signals, on the Yagi here, the 2-meter elements in this picture are horizontally polarized. And one thing I've noticed, especially if you're going to mount it on some sort of rotator, is, and I'm not sure if it's because I use metal on the mounting brackets, but the 2-meter elements work a lot better for me when they're vertically polarized instead of horizontally polarized. Not exactly sure why that is, but that's just from my experience. And then the second thing, which I would say is a little more critical, is the calibration of the rotator. So when I went out that day, I forgot to bring my magnetic compass. So I was using my phone to calibrate the rotator, zero it in. And if you, say you just take any phone and you go to 0 degrees north, and then you mark that or just line up with something, spin around in a circle, come back. now 0 degrees is here. And every time you spin around, 0 degrees is a little bit somewhere else. So, I would say that was the main problem there, is that the rotator was not calibrated to exactly 0 degrees north, and you can be a couple degrees off. I've noticed anywhere up to 4 degrees off, and it doesn't really have too much of an effect. But I would say we are at least 10 degrees off on the calibration, and the depending on the gain on your antenna, the calibration is going to be more strict. So if you have a higher gain, you're going to have a narrower beam width and need a tighter calibration. So this parabolic dish I had left over, I was kind of thinking I wanted to put it to some sort of use, and then forget where I read it, I saw people decoding the GOES weather data off the GOES 16 satellite. And I thought, that's pretty neat. I'd like to do that. So I popped the dish out, and I already had an SDR. I had a Hack RF, and I hooked it up to there, aligned it, and found the signal coming down. Excuse me. And so then I was looking for software to decode the raw I/O off the SDR. And there's a couple Linux open source versions, but I wanted to be able to maintain the station in one computer that could run all of my amateur radio software. So I was thinking about maybe putting a bootable Linux on a flash drive and then having it all set up, so basically plug and play and be able to do the SDR. But I ended up finding a gentleman. His handle is USA Satcom, and he wrote a Windows version of the GOES decoder. And so I went through a pretty haggling process with him as far as getting him to actually release me the software and let me buy the software. You think someone's selling it, oh, here you go, buy it. But he definitely put me through the ringer to get the software. So I ended up having to get a new radio, a new preamp. Right here off the lead, there's a preamp there to boot. There's basically an LNA. So there's a preamp, there's a filter, preamp, and then a filter to filter down the interference. And without the preamp in there, if you hook the radio right up to the lead, I would get about 75 to 80% signal, maybe lower, down in the 60s. And with the LNA, I get 95 up to 98% signal. So this signal here, or this image here, was one of the first ones I received when I was first calibrating the station. And then I got my calibration set pretty good, and I ended up, this year's on a gas can on a shovel or something in the front yard. And so I eventually got one of those satellite dish tripods. And then I took a mount off a DirecTV dish and mounted it. There's the bracket that's used to attach it there. I welded that onto a DirecTV calibration mount, and then put that on the tripod. So now it's pretty portable and can align it. But even this image here was decoded using that setup. So the images are about 5,000 by 5,000 pixels. So they're pretty high def. I think, don't quote me on this, I think a pixel was 5 kilometers over is about the size of the pixel. I'm not exactly sure on that, but the definition is great, and I wish I would have attached some other bands, because a satellite takes a couple different types of images and different light bands, so different infrared frequencies. So this here's a false color, or a computer generated image. And so basically it's a couple different bands stitched together and adjust the frequency a little bit to give you a false color. Some of the infrared bands are pretty neat to show the water reflectivity. So I was tracking Dorian the whole time on the satellite, and I got a pretty good picture of it right when it was coming to the coast of the Bahamas, and the thing was max force, and it was just a beautiful picture. So I think this is the end here. Let's double check. So does anybody have any questions?
Did you say that the software that you have running on the PC colorizes the image?
Correct.
Okay.
Are
Yes,
you a
sir.
member of Taper?
No, I'm not.
And you got the, under one